my talk is on exact digit categories. So here's my plan. I will start with a brief reminder on extriangulated categories. Then I'll give the motivation of the definition of exact digit categories. Then we'll give the definition of exact digit categories. Then we give the main ingredients, namely the notion of homotopy kernel pair, and the definition of exact digit categories. And we end up with some results on exact digit categories. Okay, first let me give a brief reminder on extriangulated categories. In 2019, Nakaoka and Palu introduced the notion of extriangulated categories, which generalizes the notion of equivalence exact categories in 1969 and the notion of Grothendieck various triangular categories. And the main ingredients in their definition are a additive bifunctor E, which parameterizes certain equivalences class of sequences, and a realization which assigns each element in the group, namely set delta, to an equivalent class of sequence. For example, in an exact category, we have the bifunctor E, which is just the extension group between C and A, and then the realization is the identity, which sends an element in the extension group to the associated equivalent class of conflations in the exact category. Okay, so let me give the motivation for the definition of exact digit categories. So the motivations consist of two examples. Let K be a field. So we have a Haibo Jin's category of digit Cohen-Macaulay modules over a certain algebra, namely connective. So the cohomology concentrated in non-positive degrees and proper. So the total dimension of homology is finite, and the gross thing is a certain property of A. And we also have Yilin Higgs category, which associates to each S-quiver with potential and a certain category. So the main point is that in both examples, the categories are extension closed subcategories of a certain algebraic triangular categories. Extension closed subcategory of some algebraic triangular category. So the following definition is natural. So if we consider X triangular category, then we say the X triangular category C is algebraic, provided it is equivalent to a full extension closed subcategory over an algebraic triangular category. And it turns out that this definition is equivalent to the following. So it is equivalent to that to saying that C is equivalent to a certain ideal quotient E modulo some P0, and here E is a equivalent exact category, and P0 consists of certain projective injective objects. And the third point is what we are going to talk about. It says that C is algebraic extriangulated if and only if it is equivalent to the H0 of exact digit category. So that's what we are going to talk about. Okay. So we have the following table. On the left-hand side, we have certain types of category, namely abelian category, and the triangular category, and the stable infinity category, and the pre-triangulate digit category. And except this triangular category, these three notions are properties of the category. And on the right-hand side, we have the axiomatization of an extension closed subcategory. Namely, an extension closed subcategory of an abelian category is a Yilin exact is axiomatized by an Yilin exact category, and an an extension closed subcategory of a triangular category is axiomatized by an extriangulated category in the sense of Cohen-Macaulay, and for us an subcategory of a stable infinity category is axiomatized by Barwick's notion of exact infinity category, and the axiomatization of an extension closed subcategory of a pre-triangulated DG category. So, and why do we want DG enhancement rather than when we have a topological notion of exact infinity category? And it's because that it's much easier to do computations in DG categories. So, and this suggests that we should make the form. We should complement Barwick's notion of exact infinity category to the framework of DG categories. So let me first give a quick definition of exact DG categories. So throughout this talk, our K will be a field, and our A will be a DG category such that H0 is additive. Then we give the definition of an exact DG category, which is similar to that of Quilin's exact category, except that the category that the sequences live in is more complicated. So that an exact DG structure on A is a class of homotopy kernel-corner pairs, which is similar to the ordinary kernel-corner pairs. And this notion is to be defined later. And the homotopy kernel pairs consists of a sequence such that a sequence in the DG category A such that I and P are of degree 0 and the differential of I and P are 0, and such that the composition of I and P is the differential of degree -1 H. And here I is called an inflation, and P is called a deflation, and this sequence is called a conflation. And this class of homotopy kernel-corner pairs is required to be closed under isomorphisms in a certain category to be defined later, and such that it satisfies the following axioms. So first, the identity of 0 is a deflation. So if we have this one, then this is a deflation. And second, that is that deflations are closed under composition. So if we have P to C and C to C prime, this is P, this is Q, such that P and Q are deflations, then the composition is also deflation. And we have the push out and the pull back axioms. Namely, if we have an inflation I, then for any morphism from A to an arbitrary object A prime, we have a homotopy push out, a notion to be defined later, and such that the homotopy push out of an inflation is also an inflation. And dually, we have the notion, we have if we have a deflation P and an arbitrary morphism in the DG category, in that 0 of the DG category, then we can form a homotopy pullback, and such that the homotopy pullback of a deflation is also a deflation. And if these axioms are satisfied, then we call the pair A and the class of homotopy canonical pairs an exact Dg category. So here we use a more sophisticated category of canonical pairs than equivalence than that equivalence definition. And we have examples. So if we start with an ordinary category, namely a Dg category concentrated in degree 0. So then to endow A with an exact Dg category structure is the same as to endow A with a equivalent exact structure. So this says that our notion of exact Dg structure generalizes that of equivalence notion. And furthermore, if A is a pre-triangulated Dg category, then A carries a canonical exact Dg structure. And thirdly, if we already have exact Dg category A, then any extension closed subcategory is an exact Dg category. So this notion of extension closed subcategory can be defined in a natural way. And so in the example 2 and 3, they suggested that we have a link. There should be a link between exact Dg category and the extriangulated category, because an extension closed subcategory of a pre-triangulated Dg category is if we take the H0, then we find an algebraic extriangulated category. So then we have our main ingredients in the definition of exact Dg categories. So in the above here, we have something to be defined. Here, the notion of homotopy canonical pairs and the notion of homotopy push out and homotopy pull back, and the category which these objects live in, this category. So the first thing is to define the notion of homotopy canonical pairs. And from the examples, we know that we should generalize equivalence notion of exact category. So we should our notion of homotopy canonical pairs should also generalize the ordinary canonical pairs. So if we start with an additive category, and if we want to endow A an equivalent exact structure, we should consider canonical pairs. So we have a sequence such that their composition is 0. And to say that they are canonical pairs is equivalent to saying that this sequence induces a long exact sequence for each object W in this additive category. Yes. So this is equivalent to saying that there is a left exact and plus the dual. I forgot to write. Yeah. And also we also want to generalize the notion of pre-triangulated Dg category. So we should also consider a graded split short exact sequence in a pre-triangulated Dg category. These are the key notion for Dg category to be pre-triangulated. So a sequence x to y to z is graded split, then it induces a long exact sequence. So for each object W in this Dg category, we have this long exact. Notice that here on the above, our exact sequence, we don't have this stops in home, and there's no x1. But here we have a long exact sequence which can be extended to both sides. So to generalize this, our naive definition for a sequence x to y to z and morphism at p in the DG category to be homotopy canonical kernel pairs. Homotopy canonical kernel pair is that it induces long exact sequences. So mainly we just want this part and no higher parts. So for each element W, we have this long exact sequence plus the dual. So we have ZW. We have W in the second variable. So here comes the main definition of homotopy canonical kernel pairs. Let me say that this does not work because there is a problem in this naive definition. Is that we don't have a natural connecting morphism from H-1 to H0. So we need to find such one. And let me give the main definition. So again, let A be a DG category such that its H0 is additive. And we consider the A infinity category. So the infinity functors between the this category. Namely, we have 3 objects, and there's K here, and the composition is 0 to our DG category A. And this A infinity category is a DG category because our A is a DG category. And in this category, we have objects which exactly are sequences of this form, such that our I is of degree 0 and the differential of I is 0, and our P is 0 and differential of P is 0, and we have a homotopy H of degree -1 such that the differential is the composition of P and I. And we also have morphisms, namely in the Z0 of this category, a DG category, and the non-homotopies. So we can form the homotopy category of this category. And so we have the homotopy category of 3-term, we call this the homotopy category of 3-term homotopy complexes on A. So a sequence of this form will induce a canonical diagram in the category of DG modules over A. Namely, we take the representable from DG modules and form the mapping cone of this morphism, and we can form this homotopy fiber, the shift inverse of the mapping cone of P-1. And this map I and the homotopy H will give us a morphism R from X and from the representable DG module to the homotopy fiber. And similarly, the homotopy H and the morphism P will give morphism S from the mapping cone to Z and to the representable DG module. And we say that this sequence is a homotopy kernel pair if the 2 morphisms satisfy certain property, namely the morphism R will induce a quasi-isomorphism of complexes. Here on the right hand side, we have the R home between 2 representable DG modules, and on the right hand side we have this R home, and this morphism is induced by R from this to this. And similarly for S, we have this morphism induced by S, and we require that both are quasi-isomorphisms for each element A in A So the reason for this definition is that in this way, because for this will induce a long exact sequence because we have a graded split short exact sequence here. Then it induces a long exact sequence, namely here in this case, we have a long exact sequence. Then we require that the connecting morphism from this to this is an isomorphism. So we fix the problem that appears in the naive definition here because we need this one, and this morphism is essentially provided by this by a graded split short exact sequence here. Okay. So this finishes the definition of homotopy corner pairs. And are there questions, Juna? Okay, so let me give the main results. So first, we should compare to Barrick's notion of exact infinity categories. So, namely, the connection between our notion of exact TG category and the Barrick's notion of exact infinity category is provided by a degenerate functor. So if we have an exact TG category A, then is degenerate, which is an infinity category, carries a canonical Barrick exact infinity structure. So in particular, by a result of Nakaoka and Palu, it follows that the H0 of our DG category, which is equivalent to the homotopy category of the infinity category, the degenerate of A, it carries a canonical extriangulated structure. But alternatively, we can construct this extriangulated structure on H0 of A in a direct way. And second is concerns about the derived category of our exact TG category. So this extends the equivalence exact category E, which embeds into its bounded derived category of E. So if we have an exact TG category A, then there exists a universal morphism from A to a pre-triangulated TG category in the homotopy category of the small category of DG categories, in the category of small DG categories. And it is universal among exact morphisms. So this morphism is required to preserve conflations. Okay. And this morphism set has some good properties if our DG category A is connective. So a DG category A is connective provided its cohomology is concentrated in non-positive degrees. So if our DG category A is connective, then this morphism satisfies the following property, namely it is quasi-fully phaseful. So if we take the truncation of this universal morphism, if we take the truncation, then this will be a free phase functor, and the image of this functor is an extension closed subcategory of this pre-triangulated DG category. So namely, we have a quasi-equivalence from the truncation of A to our A is already connective. So from A to the truncation of an extension closed subcategory of pre-triangulated DG category. So in particular, this shows that our H0 of A is an algebraic extriangulated category. And moreover, it is quasi-fully exact. So it is quasi-fully exact. Namely, we have a natural bijection between this E and between C and A. Here, this is the natural extriangulated structure that is given by the our remark that H0A has a canonical extriangulated structure. And we have a bijection between this abelian group and the extension 1 in this in the H0 of A, so it's a triangular category. So we have extension 1, and we call this DG category the DG derived category of A. So, and we recall an old slogan by Neumann. He says that the triangular categories do not reproduce. So in particular, extriangular categories do not reproduce. So, but in our case, if we have a DG enhancement of an extriangular category, then we could say that exact DG categories do reproduce. So to be more precise, we have functor categories and tensor categories between in the setting of exact DG categories. So if we have an exact DG category A and a small connective DG category I, then we can form the rep DG from I to A. This and this DG category carries a canonical exact DG structure, and we can also construct the tensor product of two connective exact DG categories. So if we have two connective exact DG categories, then we can form a universal exact. Exact means that if we fix a variable here, then it will send a conflation in B to this one, and similar. If we fix a variable in B, it will send conflations in A to conflations in the tensor product. And this is universal in the homotopy category of small DG categories. And we will end my talk with exact substructures. So if we are given an exact DG category A and the class S of homotopy kernel pairs, then we have the associated algebraic extriangular category H0 of A and a bifunctor E and a realization S. Then we have the following fact that we have a bijection between closed subfunctors of this functor and the exact substructures of this exact structure. So in particular, this implies that this category with this subfunctor is also an algebraic extriangulated category. And we have a lemma to produce closed subfunctors. Namely, if we have an extriangulated category, and inside this extriangulated category, we have extension closed subcategory, and then we can produce two canonical closed subfunctors. Namely, we define the closed subfunctor. We denote this subfunctor by E upper n, and it takes values between C and A in the following way: that the associated the associated E triangle is given by the images from an object in, it is given in such a way that we have an E triangle ABC, and it lives in this closed subfunctor if it can be given by a push out by some conflation which has left most object n in this extension closed subcategory. Here, this is n. Here, this is the extension closed subcategory of n, and we can prove that this is a closed subfunctor. And dually, we can define another closed subfunctor, which has we can take n to be on the left hand side. So we have two canonical. We have a simple way to produce closed subfunctors. And here's our last theorem. So if we have an exact DG category, then and it satisfies a certain set of finiteness conditions, then we can describe the lattice of exact DG substructures. But usually this is not the lattice of all exact DG structures on A. We can only talk about exact substructures of a given one, of a given exact DG structure. And these properties are the H0 of A is home finite, and the H0 of A is Schmidt and has finitely many indecomposable objects. And the most important thing is that in this extriangulated category, H0 of A with its canonical extriangulated structure, it has AR sequences in the sense of Nakaoka, Yama, and Palu. And if we have these conditions, then the lattice of exact DG substructures of A is isomorphic to the lattice of subsets of the set of AR sequences. So it is a Boolean lattice. Okay. And we have examples to illustrate exact DG substructures. So the first one is Yilin-Wu's Higgs category. So if we are given a Jacobi finite S quiver with potential Q, F, and W, then we can form the associated Ginsburg morphism. We denote this by from B to A. And then we can define the relative fundamental domain, which is a full subcategory of the perfect derived category of A. And its objects are mapping cones of two objects P and Q to A, and the morphism should satisfy a certain property that if our P from P to any object I in this frozen projectives, then we can lift this P to I to a morphism from Q to I. So this is the surjective.
Xiaofa, could you briefly remind me what this Ginsburg morphism is and what B and A are?
So this is the so this P is pi2 and the 2 caliber completion of KF. Our F is a frozen part, and to the this is 3. This is 2.
For B, it's 2.
I forgot, but this is so we have a morphism from the frozen part to this. We have an inclusion from Kf to Kq. Then this B to A is relative parallel completion of this morphism. But I'm not very familiar with the details. But I will give an example. Okay. Namely, let me insert a new page here. So if we have,
I think, yeah, if you want to, you can just continue with the talk and give the example later. And that's, I didn't want to distract you. I just wanted to know, and I think that you answered the question, so that was okay.
Okay. So we have defined a certain subcategory of the perfect derived category, and this is extension closed. So so if we take the Digi enhancement of this category, then we know that this category should carry canonical exact Digi category structure. Okay, but we can we should continue with the definition of cluster category. So we define the perfect valued category, which is a cyclic on the frozen part. So its objects are perfect valued digimodules over A, such that it is 0, 1 restricted to the frozen part. Then this is a subcategory, triangular subcategory, and we can form the radial quotient. And this is Yilin cluster, relative cluster category. And so we have this diagram. This is a full subcategory, and this pi is a radial quotient. And it is proved by Yilin that the essential image of this quotient of this subcategory is extension closed in this cluster category. And the restriction of pi to this subcategory is an equivalence of k-linear categories. So on both sides, we have extension closed subcategories of triangular categories. So when we consider their Digi enhancement, then we have so we have Digi enhancement. Then the first thing is that this functor is a shadow of a quasi-equivalence. And so since our notion of exact Digi structures can be shifted between quasi-equivalences, so we can talk about exact Digi structures on both categories. And this extension closed, and this inclusion of extension closed subcategory gives one on this side, and this extension closedness gives one on this side. And it turns out that this exact Digi structure on this left-hand side is an exact Digi substructure, and this exact Digi structure is precisely that makes the canonical object A in this category projective. So we know that if we have an arbitrary object, arbitrary class of objects in an extriangulated category, and we can take the exact substructure which makes something projective. And this is also the one that this object, if we consider its additive closure, then it is an extension closed in this extriangulated category H. And if we consider our above lemma here, we consider this. We take our n to be the additive of pi a. Then we also get the same substructure here on this DG category. And if we consider this exact structure from this one, then its DG derived category is equivalent to the perfect derived category of A up to direct sum. And if we consider this inclusion here, then its DG derived category is equivalent to the, okay, I forgot, DG is equivalent to the DG enhancement of the cluster category, the relative cluster category, up to Dirac sum. And we have a last example. So this illustrates our last theorem. So if we consider the algebra of Ka2 and our DG category A is the DG enhancement of the two-term complexes over projective A modules, finitely generated projective A modules. Then our A is an extension closed subcategory of this pre-triangulated DG category, CBDG approach A. So our A inherits a canonical exact DG structure. And we have this AR sequence for this exact DG structure. So namely, this is AR sequence, this is an AR sequence, and this is an AR sequence. So we have these three. And if we consider conflations, E triangles between indecomposables, there are another two special one from P2 to the shift of P2, which is given by the identity of shift P2, and the same for P1. And it turns out that the lattice of the exact DG substructures is given as follows. So here we have the split one, and here we have this canonical exact DG structure. Have this. These covers the subsets of the set of AR sequences, and so in this case, these two cannot be given by extension closed subcategory of our exact DG category A. Here, this is canonical exact DG structure, and the other six, they are except these two are given by certain extension closed subcategories, which is given by this lemma. And here I want to say that in this, if we consider this set of AR sequences, then our beta also included. It also belongs to this exact DG substructure, and for this, our mu also belongs to this set, this exact DG substructure. Okay, and another thing is to say is that since our algebra A is hereditary, these are all the exact structures on this DG category A. Okay. And I think I'll stop here.